Every day, around 95 million photos and videos are shared on Instagram. Billions of messages and notifications are sent every single day. So every single one of these notifications, like Sarah liked your photo or Mike commented on your post, had to reach the right device at the right time without delay. Now, imagine one configuration change, one retry bug, one cascading failure. Suddenly, billions of daily notifications don't arrive, revenue stops, engagement drops, users wonder, what's going on? Is this app broken? So someone has to keep that running. Someone has to catch these failures before they cascade. Someone has to make the decision like, do we intentionally take the system down 100% to fix it faster? Or do we let 30% of our users suffer for 12 hours? That's the job of a site reliability engineer. And today's guest, Vlad Leyberov, has spent his career doing exactly that at Google, Meta, and Amazon, systems operating at billions of requests per second. These systems are the ones we use every single day, systems where even a small mistake can have massive global consequences.
It's quite difficult to comprehend, especially at large scale, how cascading failures could propagate throughout the system. What I've observed over the years of working on large distributed systems, that their behavior is unpredictable. Even a little change, if we don't fully understand how cascading failures propagate, will have absolutely catastrophic consequences.
This episode is a conversation about what it actually takes to keep the internet running when failure just simply is not an option.
So that kind of stuck with me, that sometimes you have to make the situation worse to make it better faster. Intentionally causing 100% outage up to this point, I don't think ever crossed my mind on any system. There is always this instinct, but we must preserve at least some customer experience. 100% outage is the worst possible scenario. Well, not always. Sometimes 100% outage for a short period of time is better than a rolling 30% outage that is going to last 12 hours.
So it's so nice to see you, Vlad, since the Google SRE New York City Tech Talk. Thank you for having me. I know that's also something that you lead and do.
It's been a pleasure, Alexa. Good to see you.
So I'm really excited to talk to you about reliability and scale because I feel like you have a lot of great experience when that's concerned. So I want to just take a step back here and talk about the scale. So for people who don't know, PubSub, we're talking like billions of messages per second, tier 1 infrastructure, outages that could go into cascade into different Google services and customer systems, very strict SLOs, and very rapid incident response expectations. And like for Meta and Instagram, you worked with their notifications. So that's something around 40 billion notifications per day. Correct
Give
me?
or take it.
Yeah.
It was 5 years ago, probably more now.
Yeah. And that's directly tied to, their engagement, their revenue. And then you worked on the Alexa API, right?
Indeed.
At Amazon. Funny that my name's Alexa. I always thought it'd be funny for me to work at the Alexa team. How that work out. I think someone reached out to me once a long time ago and I actually replied like this would be funny. But that also has, millions, hundreds of millions of devices that have real-time user expectations. So you've worked on systems where even something small can have a massive impact. What is something about reliability at scale that you find many people still don't fully understand or grasp, even maybe some experienced engineers?
Yeah. And maybe it's not like, maybe not understanding is not quite the right angle to look at it, but I think it's quite difficult to comprehend, especially at large scale, how cascading failures could propagate throughout the system. What I've observed over the years of working on large distributed systems, that their behavior is unpredictable. The way systems communicate with each other, send messages, receive messages, scale, don't scale, fail, right? It's more akin to natural, like nature, what happens in natural, in oceans or in parks, right? Little things can have cascading effect that could lead to really dramatic results. And to your point, even a little change, if we don't fully understand how cascading failures will propagate, will have absolutely catastrophic consequences. I actually have a recent example from last week, no less, where one of our systems, the Google Cloud Build, unfortunately had an outage. It's not a secret. It's been like, we, of course, fully transparent. We published that and communicate that with our customers. So what was happening there, like say, is the way cloud build works at a very high level. So customers keep their source code in Git or GitHub to be precise, right? When they make a change, we receive a webhook event, and then we go ahead, pull the code, build, and then the build pipeline does whatever needs to be done with the build artifacts. So we had a customer, a large customer, institutional customer, who was performing a migration from GitHub to GitHub Enterprise, which is like a slightly different product that we offer. And they were sending a large number of events. Normally, we would have coped with it just fine because our systems scale. GitHub itself scales horizontally. But what happened was customer had a misconfiguration, and all of their requests resulted in a 403. So it's authentication failure, right? And we did not unfortunately, treat that particular type of response correctly. So we retried. Our systems tried to self-heal, so they retried. And at the same time, we were running quite close to our quota limits for some of our internal systems. And the way we treat the customer requests is we're a global system, so it's a global service. We run in all of the regions that Google supports, provides to our customers in GCP. And we never know where the particular artifact is going to be needed. So what happens, we start pulling in all the regions, right? And then if there is a project in that region for a customer, then the build pipeline kicks in. But because requests were failing, we kept retrying. So if you can imagine, let's say, you have 1,200 requests a second, not a big deal. But then you multiply that by the number of regions. And then you multiply that by the aggressive retry mechanism that we had within our systems because we want to be helpful. So what happened is that the pipeline kept retrying, number of requests quickly accelerated to hundreds of thousands, and then our internal protection mechanisms kicked in that we didn't realize would have at this point, and then they stopped outgoing requests for all of our customers. So that cascading failure was novel. We never quite experienced that type of authentication failure request that they scaled before. So we've learned something new, which is good outcome, of course. I mean, unfortunately, that the incident lasted a couple of hours before we mitigated it. But yes, that particular chain of events was very hard to predict. Even if you just look at the event propagation graph, you kind of think, not a big deal. We respond, right? But then you multiply it by the number of times we repeat, and that cascades into a catastrophic failure, unfortunately.
Yeah, that's such an interesting story. Can you tell me about what does a 2-hour downtime mean in this context? What were the implications of that?
Yeah, sure. So for our customers, what it meant that they could not do any new builds. Basically, all of their existing systems, of course, kept running. Like existing artifacts in production were not affected. It's just they couldn't perform a pull request and do a build. So not the end of the world, perhaps. Of course, it's a negative experience for our customers, and we're doing our best to make sure doesn't happen again. So what we've learned is that first of all, we need to treat negative requests, negative responses, just as we treat positive responses. And what I mean by that is, so successful authentication, right? We cache it, and then for the next hour or whatever, we are going to use it to communicate with GitHub. For negative responses, we didn't. And that triggered the cascading aggressive retry logic. If we did, we would have never requested it again, and that would have been fine. So that was one learning. Second learning was the aggressive retry logic. So we obviously need to revise how we address that within our internal systems. The third logic, perhaps the fan out to multiple regions, that is intentional. But again, for negative responses like that, we probably shouldn't do that, because what's the point if we never actually manage to authenticate on customers' behalf? So that was an interesting experience. Architecturally, of course, quite interesting to observe how that pipeline kind of propagated across our systems.
Yeah, and if you're running so much at scale, I'm curious, what does this repair look like? What is the what do they call it? The war room look like?
Our response procedures kicked in as expected. So it happened during the night. So our European on-callers took the page. Like we had metrics, we had alerts, so they all fired all at once. So we have hundreds of alerts failing. Of course, responders immediately realized, oh, stuff is hitting the fan. So we've got to initiate our mass outage mitigation processes. So they paged in the appropriate people who needed to be in the call. So it was all virtual. We do have physical panic rooms still, like in a catastrophic event where the internet is down, right? You could actually physically drive to an office and plug your laptop into a physical network, and you could get connectivity to our infrastructure that way. That wasn't the case. It was a virtual war room. We had representatives from SRE. Obviously, we had our development partners representatives. We paged them in to understand more deeply what could have been going wrong. We had communicated with GitHub as well, so they joined to help us figure out what was going on, where the fault is happening. And we had representatives from our external customer communication group who took on their role communicating with our customers and organizing, coordinating the response. So everyone got their roles assigned. We're like firemen. We practice for those types of events. So training kicked in.
Yeah.
Everybody did their jobs.
It seems very efficient and very organized. I'm sure you've been in a lot of these events where you're trying to repair a system that's broken. Can you walk me through generally what your mindset is when you're pulled in? Like what are the first few things that you do?
We really need to understand where the failure is coming from so we can mitigate at that point. Yes, shutting the whole system down certainly was one of the options that we have seriously considered, but we also observed that the failure wasn't 100%. So we thought, okay, fine. Some of the requests are still succeeding, so we are able to maintain at least some positive experience for our customers. So let's not do that. And then you just kind of like, understanding of the systems that you're working on is still absolutely critical. That's why SREs kind of work very closely with the dev partner teams, and we always have the option of paging in our dev partners who are the subject matter experts in their particular systems. So looking at our metrics, which we have a lot of, we start narrowing down what the problem area is. So we observe, okay, those are authorization denial requests. So why? Are they coming from the same customer? Are they coming from multiple customers? Why do we have so many requests? Is it abnormal? Is it a runaway job? Right? So by narrowing down, we finally understood that yes, it was just a single customer who were doing this mass exercise. We didn't know it was a configuration problem on their behalf, and it doesn't matter. Something is not working for them, everybody else is fine. So and mitigation measures ultimately revolved around communicating with that customer and actually working with them to stop the flood of events.
It's nice that your system was so resilient. So I know we kind of dug into an incident there, but I do want to take a step back and just want you to explain a bit of your journey. I was looking up on LinkedIn some things that you've done. You work for the Salvation Army. That's pretty cool. And also I saw you have a business degree.
Yes, it's been a long journey.
Yeah, tell me more about that.
Yeah, sure. Yes, I do have a business degree. I finished my college in Australia a long time ago, but I've always had interest in information technology when, growing up in the USSR and then studying in Maritime Academy after school. I always liked coding. I've never had a personal computer until I actually moved to Australia and started college there. But I had a programmable calculator, so I used that to kind of tinker and write very basic programs to process some mathematical equations that we needed to do for my Maritime Academy courses. And back then, what was popular or perceived as in demand was very different. Back in early 2000s, being an accountant was all the rage. Before that, because who doesn't need more accountants, right? Everybody wants to count money. Before that, business was kind of like the default go-to. Well, you should be a businessman. You should go and develop something, bring value to society. So that's kind of like why I didn't really make any conscientious decisions at that point. I think I just thought, well, that sounds like a great idea. I'll go do that. But yet I took as many information technology subjects or units as I could. I didn't quite get enough points to graduate with a double major, but I did accumulate quite a few when I finished my degree. And I worked actually in business for a small import-export company in Sydney, in Australia, for a couple of years before a friend of mine started a startup. It was an IT consultancy, a company in Sydney, and we've studied in college. He was doing his master's degree at the time. I was still doing my undergraduate, but we've been very good friends for many years. And he thought, why don't you join my startup and see how you go? So I did. So the rest is history. So I've learned all I know on the job, so to speak. Started with some database reporting, and then Java, and then other things.
That's fascinating. And you start off at the startup, but now you've worked at some pretty big companies that I mentioned in the intro, like Amazon, Meta, and Google. So can you talk to me about each of those experiences and how they shaped how you think about reliability today?
Yes. Well, I think, and I know some of the things might sound a little cliche and like, drinking our own Kool-Aid. But customer obsession at Amazon, I'll start with Amazon because that was my first big tech company, is a real thing. Like, it's ingrained in people's psyche. It's ingrained in their day-to-day. That's how they approach literally every single task they have. Everything starts with the customer. So I think my obsession with reliability really started there. At Amazon, no matter how, is it a single customer being affected? Is it not a big customer being affected? Somebody is going to get paged. And we will work in the middle of the night trying to fix that particular incident if a customer is in pain. Amazon, so first of all three companies really run reliability quite differently. Amazon is famously running DevOps. So every product team runs their own ops. They're all on call for the service. There isn't a central operations team, so to speak, right? Everybody does their own thing, and all services run on AWS. So, well, maybe it's not entirely true, but most of them run on AWS. So there isn't a central outside of AWS team. It was an intentional decision by Amazon back in 2012, 2014 that we have to use our own software to run the company. Otherwise, that's how we make it better ultimately for our customers and for ourselves. There is no internal APIs. There is no special treatment, special quotas, right? Everyone is a customer. Doesn't matter, external, internal, same treatment. That is like, I think, quite a good approach to reliability. It shouldn't matter what is failing. If the failure is real, if there is customer impact, internal or external, we have to react. Meta is structured very differently. So in Meta, there is literally an organization called the Central Platform. That's exactly what they do. It's like the corporate IT, so to speak. But Meta is in a slightly different scenario. They don't have a lot of publicly facing services or applications. I mean, there is Instagram, there is Facebook, WhatsApp, maybe 2 or 3 more. So their operations are streamlined, starting from design of the hardware and data centers to run those very few types of applications, and they are very, very good at it. So they design from the hardware, from the chip, how to streamline processing of images or messages, right? And they have specialist teams dedicated to that. So they may not know much about application logic or the structure of the binary. Their job is to make sure it runs on the hardware that is designed for it, and it is scalable and reliable. There is very few interactions really with a central platform team. It's kind of like you submit your artifact, it gets deployed, you have some observability, and that's kind of it. There isn't a lot of exchange of information unless something goes wrong. Then central platform team might reach out, or they might page you and try to work out what if it's a particular route. At Google, SRE is kind of like a core engineering principle. Google philosophy. Google designed SRE 20 odd years ago as a separate engineering discipline, and there is a very close collaboration between. There is separation of concern, but also very close collaboration between SRE and the dev partners. So, like again, at Amazon, everyone is SRE and a dev partner. At Facebook, there is two different camps. At Google, it's a partnership, separate specialization areas of expertise, but still a very, very close partnership to deliver customer experience to us. So yeah, I think being at Amazon really shaped my empathy, I guess, with the customers. Like I feel very strongly when, our customers are suffering, that something is not working. We have to do something. Doesn't matter, big, small. Like we have to react. I think that's why I enjoy my role as an SRE. I feel it is my duty to ensure customers have a good time with our products, and that's how I view how we measure our success. I'm sure you've read SRE books, and you've come across the term critical user journey, which is kind of like an extension of your traditional SLO definition. So a critical user journey is really supposed to represent customer experience as they experience our product, as the product description, so to speak. And when that breaks, we need to measure the whole experience, not just is the latency good, is availability good. All of the signals in themselves are great, but we need to kind of put them together to construct a customer experience. If one of them is breaking, then the whole customer experience might be broken. Then, even though the rest of the indicators are great, customers are still having a bad time with our product. So that's kind of like how we, I think, transitioning within SRE at Google to view our success.
So it's like a group of service level objectives that create some sort of score in a way?
Exactly. Well, it could be a single measure, but it has to capture a end-to-end experience by the customer. Let's say, for example, pops up, right? So it's a relatively straightforward experience. And in isolation, you could view something like, okay, how long does it take to publish a message? How long does it take to subscribe a message? What's the throughput? What's the latency? Right? So those are SLOs. But the customer experience, CUJ, might be, as a customer, I will create my topic first. Then I will create my subscriber. Then I will publish a message to the topic, and then I subscribe at the other end. And that's my critical user journey. So we need to measure how long does the whole thing takes. Is it reliable? Is it too slow? So that's kind of like, yes, it's a combination of multiple SLOs.
Oh, I like that. And it takes a lot of work to set all that up, all that observability too.
Yeah, it's typically, it's like script, I guess, is not the right. It's like a little robot, that goes and exercises those types of experiences over and over again, and then we emit a metric.
You did already bring up a incident that happened, but I'm curious about an incident that really sticks with you until now. What incident have you been through, or a moment that really changed how you were thinking about reliability and system design?
Yes. I can think of one. It happened at my days at Amazon Alexa, actually. When we're talking back, I don't know, 2018, probably. And it's all publicly available. It was a well-documented outage. So at a high level, what happened? Devices communicate with the backend, right? But device is a self-contained system. It has a version of Linux running on it. It communicates with the backend and publishes metadata about the device itself, so that the backend systems know how to interact with it, like what capabilities it has. Does it have a camera, the microphone, etc. There's like hundreds of multiple elements. So what happened? A particular update on devices caused what is commonly known as a poison pill situation. So corrupted devices started writing corrupt records into the backend, so the backend couldn't communicate to the devices anymore, right? And it doesn't happen all at once. So it was a gradual rollout. So if you can imagine, devices are receiving an update, they communicate with the backend, and then they go dark. And so it happened overnight. So I don't know what time of night it was, 1 a.m., 2 a.m. maybe. I'm not sure. So it was daytime somewhere, probably in Asia, where the upgrades started happening. So we get alerted, right? We have now 20-30% of our devices, maybe less at the time. We've lost comms with them. However, devices are designed to self-heal. So when they lose communication with the service, with the backend service, they perform like automated mitigative options on the device itself. So they will eventually heal. So they will go back to the previous version and they will self-mitigate. But that's going to take hours. So we have a scenario where we have like 20-30% of devices out. And it's like a rolling wave of due to the corrupt record in our database. So we obviously, joined a war room. At the time, it was just a phone conference. There was no Zoom. So we were all on the phone, for like 2 or 3 hours. We're trying to work out what can we do. And like there isn't a good solution because you can't trigger that on all the devices at the same time. It's very difficult to do. It will require us implementing something new, potentially maybe causing a worse situation. And then a suggestion, one like engineer suggested, why don't we drop the table? And we're talking about DynamoDB, right? DynamoDB is a key value pair distributed store. It's fantastic system. We're talking about a sub 10 millisecond response, absolutely magic. It's phenomenal. So yeah, the suggestion was drop the table, clear out, let devices sync. And that of course will cause 100% outage, because then none of the devices are going to communicate with the backend, but they will resync maybe after a few minutes, right? And we'll create new, not corrupt records in the database. So that kind of stuck with me, that sometimes you have to make the situation worse to make it better faster. Intentionally causing 100% outage up to this point, I don't think ever crossed my mind on any system. There is always this instinct, but we must preserve at least some customer experience. 100% outage is the worst possible scenario. Well, not always. Sometimes 100% outage for a short period of time is better than a rolling 30% outage that is going to last 12 hours.
Wow, that's a great takeaway. That's a really good point.
Yeah.
Have there been times when you need to just shut everything down?
Yeah, well, not at 100%, but definitely if there is an unavailability or some situation that is happening at a particular region, like we would go ahead and just drain out of that region, meaning that we will stop our service in that region completely until the situation corrects itself or we perform corrective actions. I guess a consistently bad experience is better than inconsistently bad experience.
That's very true. I also want to keep talking about the realities of running things at scale, problems like this. To be honest, most developers, even most professionals, don't really face this type of scale nor the uptime requirements that you have. I think these are the best problems in engineering when you need to solve for these. And most people just don't need that. From your experience, though, what do you think is different about processes that allow these large teams to meet these requirements versus how they would maybe operate a system that had less challenging requirements?
Well, I think rigor and discipline when it comes to observability, early detection is absolutely necessary. So Google GCP had a massive outage last summer, very well documented. The entirety of GCP basically went dark for maybe 2 or 3 hours. And it was due to a config change that propagated everywhere all at once and kind of broke everything all at once. So that was a painful learning experience for us as a company. And what I think we've learned, well, not I think, that's kind of like kicked off a response. We're still working through that we must be able to, first of all, we must not make changes everywhere all at once. There are very, very few exceptions that I can think of that will require that. Configuration changes specifically. And we must catch any breaking changes early. So the way we perform our rollouts now are quite a lot more disciplined than what we used to do back before summer 2025. I think, of course, some processes and best practices standards existed, but now it's like you can't operate your service until you meet those requirements. It's very, very strict. So I think that's what most services may not realize, that like rigor and discipline when it comes to running production systems at scale, because even small outage somewhere could have a potentially devastating cascading effects, as we talked about earlier. So catching those things very early, preferably with no customer impact, but a little bit customer impact is still, and stopping it right there is better than 100% out global outage.
Yeah.
It will take a long time to correct.
Most people would think of that as a slower process. How do you balance meeting all these requirements and meeting all these rules with also developing and pushing quickly?
It is a slow process. Yes, it was a deliberate trade-off. We will trade off velocity for stability and early detection. And I think it's a right call. So typically when incidents like that happen, it's like the pendulum, that swings fast, go fast, breakneck speed, then, oh, no, slow everything down. So we kind of like went back the other way. But now we are starting to obviously learn, all right, so what is safe? Like what is fast but still slow enough to allow us to catch those kind of incidents early. So we're learning on our experience as we go. We haven't experienced it before at our scale. I don't think anybody has. So we are observing, we're learning how fast can we go. Is 8 hours enough in wave 0? Maybe 4 hours is enough. So it will continue. We will continue tweaking that to figure out what is the fastest we can go before we start slipping through breaking changes to like later waves that will affect greater number of customers. It's an experimentation process.
And how do you think about this differently when it's infrastructure versus a customer-facing product?
I don't think about it differently. Changes to infrastructure need to happen gradually as well as the product binary rollout. Like if we want to introduce a new type of platform or update to a platform, like PubSub is a good example. It's kind of both. It's a platform that runs, I don't know, many Google products internally, but it is also a customer-facing service. So we will treat exactly the same. Changes to a platform need to propagate slowly or slower, gradually, and we have to catch breaking changes early enough. And the reason you might think, well, why don't you just run more tests or have more probers or what have you? But the reality is, at our scale, and that's something that also people learn operating systems at large scale, there are so many different variations of cases, user experiences. No amount of probers will be sufficient enough. There will always be something that we will miss. So we accept it, but we have to mitigate that by observing our systems in the wild for a little bit before letting that change propagate further.
Are there any other trade-offs that you've had to consider that are worth noting?
Yes. So consistency versus speed. That's an interesting observation that we've learned as SREs at Google. You would intuitively think that faster API response, for example, is always best, right? Every API needs to be as fast as possible. But what happens is some APIs can't be for whatever reason. Maybe it needs to process some kind of synchronous request, or maybe the size of the request is simply too large, or the logic is too complex. And when you think about how customers interact with our APIs, we found that consistency with response time is better than some APIs being incredibly fast, some APIs being incredibly slow. So if you average it out, it leads to a better customer experience overall because it's predictable. Yeah.
That makes sense. And since you've seen so many systems that have scaled up, when these systems start to scale, what have you seen that usually always becomes the biggest problem?
Like, so different things depending on the system, really. People think sometimes database is the biggest problem, and it can be if you don't have caching or some sort of middle layer that takes a lot of sharding, having everything in one location versus multiple locations. Things like networking come into play. That's probably the last thing you think about. Like, how could you possibly run out of bandwidth or IP addresses? But you can. So yes, that happens sometimes.
Isn't there a meme that it's always DNS?
Yeah. It's always DNS. It's always the DNS. That's right. So there isn't really one thing that breaks at scale. Multiple things break at scale, depending on what the system is intended to do. Well, for PubSub, I think the way it is designed is absolutely fascinating. It's a topic of multi-day conversation. But I think earlier on, when that was built, the networking optimization was probably the key. So the way the system was designed is to really take advantage of close proximity of various systems within a single cell, so that we absolutely minimize time and the network bandwidth. So we don't have to send our requests across the Atlantic. We could process them locally and then maybe send a batch. So that must have been the limitation back then when the bandwidth was more constrained.
Yeah. And speaking of evolution of things that have been problems like databases and distributed systems, and I feel like there's always an evolving new biggest problem area. And now I would say maybe it's AI, right? A lot of engineers are building systems that look similar to large-scale distributed systems we've built before and things that you've worked on for years. Where do you think there are any differences, or where AI engineers are maybe underestimating this complexity of running these largely distributed systems in production?
I think, so actually you're making a very good point. I think the ease with which we now can create highly complex systems, it's the biggest danger. We spoke about cascading failures and unpredictability of system behavior at scale, right? I think that has now become very, very easy to trip over, because AI can go and generate millions of lines of code and subsystems in minutes or hours. And interactions between the various components are usually not well understood because people just assume AI is going to do the right thing. So I think it's a great tool. I firmly believe that AI-driven development is going to be the future, and AI-driven SRE response is going to be the future. But we have to make sure that we observe the desire to limit complexity of our systems intentionally. Like, maybe, I don't know, when you construct your prompt, tell the system, hey, optimize for simplicity. Don't go nuts. Don't create something that is unnecessarily complex, even though it maybe is mimicking a large system that is documented somewhere and it's doing a similar thing. We encourage simplicity first. Create a simple system, see how it goes, minimum viable product, right? And then you can build complexity on top of that if necessary, if the system delivers the result that you expect, but then you can complicate it further to scale it. There's actually, speaking of complexity, there is an interesting architectural software design principle called the Tesla law. Not Musk's Tesla with an ER then. And what the law states in a nutshell is that in any software system, there is always a degree of complexity that cannot be engineered away. It can only be moved around. So, which is true. Like, think of cloud computing, right? You think, PubSub. How much simpler could it be? It's a two API call interaction, right? But under the hood, it's so much machinery. So yes, we've removed complexity of that message propagation and distribution away from the customers, but we tuck it under the Google Cloud infrastructure. So yes, some degree of complexity will always exist. Finding and I think it's necessary to limit that to absolute minimum to begin with. AI or not AI, doesn't matter. With AI, it just becomes easier to overlook that degree of complexity increases because, you don't really think maybe as deeply about design and system optimization before shipping code.
Yeah.
That might become a problem for some systems.
Yeah, that's a good point. I think also the complexity of how all the agents and tools interact with data, similar distributed system, but is something that people maybe could be underestimating the complexity of how easy it is, like you said, to just use all these tools. If you're trying to build your own system, there's quite a bit of complexity that adds too.
Yeah, absolutely.
And I've said this a few times on the podcast, but I do like the saying. It was a motto for a while at the first company I worked at, and it was as simple as possible, as powerful as necessary. I always think it really stuck with me, that motto.
Yeah, at Amazon, actually, we had something very similar. It's called a tracer bullet concept. So when you design a system, implement one customer experience, one CUJ, but end to end, right? So you can see all the components that you need behaving like in sequence, and then you build it out to add more functionality to the system. Yeah, I really like that approach.
Has AI changed the way that you work and operate? Are you using AI a lot every day?
Yes, we do. For everything, really.
It's crazy how much our jobs have changed in the last year, no?
It's amazing. It's absolutely phenomenal to watch. But I don't think core principles of SRE have changed. We still have essentially the same job. We're still responsible for reliability, availability, efficiency of our systems. But I think what AI has given us really is better tooling in some cases that we can now employ, and it's much easier to get the grasp of an unfamiliar component through AI than it would have taken me, for example, a few days to read a complex bit of code and understand how different components interact. Now I can just ask, hey, explain it to me in a diagram, and we'll go and do it. So when I'm debugging an unfamiliar system, I think it becomes much easier and much more efficient for me. Or even making a change. If I make a change, again, going back to like cascading effects, right? If I intentionally also mention in the prompt, say, figure out the whole like a graph where this call is going to go, and tell me what multiple components is going to touch. Yes, if we find a few cases where we would have overlooked something in the past.
Yeah, it's so powerful, especially for understanding that wide context and helping. I also use it in that way. It's the best. Speaking of AI, I saw that you're into sci-fi.
I am, yes, I do. I do love sci-fi.
I also love sci-fi. Do you think sci-fi at all has influenced how you build or think about systems?
Definitely. I think fascination with technology comes from there when you talk about human interaction with software or with automated systems, with machines in the most broadest of terms. I think it's always been very persistent throughout the sci-fi genre. I mean, yes, there's some sci-fi movies or books that kind of that. The Arrival is a good example of a sci-fi movie where it's nothing to do with software or machinery. Really, it's all about philosophy and perception of time. But yes, I do love AI. I can see a lot of examples in the sci-fi movies or books. In Odyssey 2001, the classic. I'm sorry, Dave, I cannot let you do that, right?
Yeah, I was about to ask you, are there any stories that stuck with you that feel surprisingly true and close to how these systems behave. Maybe that's one now.
Well, hopefully, HAL 9000 is not going to eventuate.
Yeah.
We built in enough, guardrails into our AIs that they will never overpower a human will. But there's definitely parallels with what we or what creators have predicted in modern distributed systems. I always thought, well, you might have heard the internal system that we run our components on at Google is called Borg. So Borg was the I should say, inspiration for Kubernetes, something Google created, many years ago, and it's still evolving. And if you watch Star Trek, of course, you're familiar with Borg society, right? And it's kind of like, now that I think about it more deeply, it's exactly the same. If you think the Borg in Star Trek is a distributed system, you have the individuals are no longer individuals; they're part of the collective. Each one of them is infinitely replaceable. Each one performs a task that anyone can perform. They communicate with the central, command, whatever you want to call it. Right? They're all aware when something happens somewhere else. That's a very classic example of a distributed system.
That's a great observation. I really liked Asimov's books. I liked how he explained the organic robots. He was a physicist, and I felt like it was so grounded in physics and what could happen. And now we can grow skin and do those things. So I'm sure that like something like that is coming. And I think sci-fi sparks imagination. Snow Crash, of course, is an amazing one. I do like the idea of the metaverse. I don't think we've gotten there yet.
I don't know. I think, Meta kind of has given up on metaverse at this point. Despite the investment, they couldn't quite think. I think there is something special about interactions, in real world that no artificial simulator can really ever replace. And of course, Matrix did, but I don't think it was willing interaction that kind of forced humanity into that.
You're right. Or maybe they're a little bit too ahead of their time, or maybe it's just like an idea that's not going to take off. We'll see. But it's definitely interesting, and I also love sci-fi, so I wanted to ask you about it. I also have a few like rapid fire questions to ask you, and so the first one, I'll just start. An example of a way that you use AI in your daily life.
I use AI for facts, not facts finding. How could I describe it? Information interrogation. So, for instance, if I know like answers are somewhere in this set of sources, right? So instead of like just reading through them all, I would add them to my notebook, right? And then I would ask AI questions. So and it makes it easier, of course, for AI too, because now it has a very constrained scope. So it will go and find answers to me. Like a good example, actually.
Notebook LLM, right?
Yeah, Notebook. Yeah. That's right. So a good example from the outage I mentioned earlier, we had with Google Cloud Build. So we would use Gemini to take notes, right? And notes document from 3 hours of meeting is going to be 150 pages long. So reading through that is going to take forever. So you just ask AI, then, hey, tell me when this was discussed and what was the outcome, and it would go ahead and do that. And that's such a time saver, especially when you're writing a postmortem analysis and trying to learn what happened. It's a big efficiency and productivity booster for me.
For sure. And what's an opinion or maybe a hot take about reliability that some engineers may not agree with?
Yeah, I think we talk about very, very hot, not hot, very, very often hotly debated concept of greenfields development versus maintenance. So in reliability, we kind of have a saying that all software development is maintenance software development. Mm-hmm. At some point, a couple of months down the track, even if it's a greenfields development, you're going to start to have to maintain what it is. So I think the takeaway, the morale of that is that before you think of replacing a system, Like really try fixing what you have. It's going to be cheaper. It will have some kind of history that you probably don't understand, but it's still necessary. Unless you replace 100% of the functionality, regardless of whether you think it's needed or not, because inevitably somebody does need it, and you'll cause a bad customer experience, try to fix existing components.
Yeah, developers are very commonly known to want to write something new rather than fix something old.
Yeah, it often comes from not understanding what the system does, and they'll go, well, the code's too complex. And actually, tangentially, well, not tangentially, very much directly related, AI makes this much easier because now maintenance is much, much cheaper. If I have to do a refactoring instead of, refactoring hundreds of classes by hand, I can now tell an agent to go and do it for me, and to do it happily, repeatedly, with predictable results.
That's so true. And what reliability concept do you think is a bit overrated?
Overrated. Not pride, but constant desire to drive a higher number of nines. My availability is 5 nines, so right? Every 9 is in operating costs and development expense. Before we decide to add yet another 9 to our reliability metric, I think we should really understand if it's necessary. Maybe our customers are happy with the number of 9s we already have. Chances are they probably are. So before we go, like, hey, let's make it faster. Like, but do we need to? Like, what's the problem here? Let's try to understand the customer experience. What's a critical user journey that will benefit from this? Is it really critical?
That's a great point. And is there a concept, a reliability concept that you think is underrated?
Yes. I often, well, especially now that I'm working at Google on such large systems, I think not realizing that the global systems will also fail globally, everywhere all at once, is something that is often overlooked. It feels desirable to let's launch our system everywhere, and all functionality is available to everybody all at once at the same time. But that has a downside of all failures are also affecting everybody all at once at the same time. So as much as we want to have that customer experience, maybe we're underestimating the possibility of a failure until it happens. And then we realize, oh, now we've caused a much more noticeable negative impact to our customers than a couple of days wait time could have.
And what's one thing that you think engineers tend to ignore that matters more than they think?
So I kind of like thought about it a little bit. Simple change management, and not just as a release management or configuration changes, just in code. So engineers try to optimize their code as much as possible, the fewer lines of code as possible. Right? Let's string all the requests all at once. Make it efficient, make it fast, take less memory. All understandable. But when systems behave asynchronously, which they do most of the time now in a distributed systems environment, I like to encourage engineers to break those changes in separate steps. For instance, if you're creating a list and then destroy it in a different step after validating that is no longer necessary. Because chances are something somewhere still wants to read that list that is now destroyed, and you end up with a good old null pointer exception, which is going to be very hard to debug and fix on the fly. So it's like as painful as it might seem, because now you have more code, you have more unit tests, your code is slower. It is going to be more reliable if you perform a validation after each step. First of all, break those operations into multiple steps and validate after each step.
That's great advice. And I've definitely been burnt by it before and learned my lesson also. So it's a situation that people run into more than you think. What's a thing that developers think matters more than it does?
Yeah, we kind of talked about the velocity of change a little bit. Everybody thinks we need to go faster. We need to go, we need to continuously ship something. CI/CD was the buzzword. At the moment, I think we're realizing that maybe that's not it's not always a desirable outcome. I think it doesn't matter. Yeah, I think kind of mentioned already a little bit. Functionality releases on a continuous basis, I think not as important to our customers as we think they are.
Yeah.
I think they're quite happy with the experience that they have. Yes, change and evolution is necessary, but it doesn't have to be at a rapid pace all the time.
Yeah, that makes sense. And I'll ask you, the last one I ask you will be a little bit fun. It'll be about sci-fi. So what's your favorite sci-fi book and or movie?
Well, I have many. I have read, I think my favorite at the moment, I've read a book called Three-Body Problem.
Yeah.
Recently, there is a Netflix series based on the first book, which is loosely based on the book, very loosely, but still pretty good series. I think that trilogy is kind of like, it's both scientifically grounded because he talks about, physics of the universe, speed of light, multiple dimensionality of the universe, etc. But it's also very philosophical. So he talks about like human evolution and beyond human evolution of multi-galactic species, how they may be interacting with each other. I'm not going to spoil it for you and or people who haven't read the book yet, but it's like the last book, The Dark Forest, is very, very interesting.
It's fascinating. I read the first book. I heard it gets even better. So I think I need to read the next one.
Oh, do it. You will do it in a couple of days. It's once you start, you can't put it down.
Those are dangerous. I definitely get into books like that too. Well, that's all I have today. Thank you so much for coming on. This was an amazing conversation. I feel like I learned so much from it. Are there any last words or piece of advice that you would like to give the listeners?
Yeah, reliability is the most important feature of any product.
Yeah.
Just a reminder.
I love that. Well, thank you so much. And thanks for coming on.
Thank you, Alexa. Thank you for hosting.
Thank you so much for listening to Alexa's Input AI. And if you want to follow along with my new episodes, writing, content, everything I'm building, you can find me at alexagriffith.com, on Substack, on YouTube, or wherever you listen to podcasts. If you enjoy this conversation, it would mean a lot if you subscribe, shared this episode with a friend, left a quick rating or a comment to help more people to discover the show and keep these conversations going. Again, I'm really grateful you're here. This podcast started as a side project for me a few years ago, and every listener who reaches out or keeps coming back reminds me exactly why I love doing this, and I love putting so much time into it. I hope this episode gave you something to think about, something to talk about. So always stay curious, stay grounded, and I hope to see you next time. Thank you for your support.